Hello again. Why don't we work on some electrostatics exercises? Let's warm up with a simple Coulomb problem here. We've got one charge, -1 Coulomb, which is 3 meters away from a positive charge, 2 coulombs. Can you calculate the force between these two and describe whether it is attractive or repulsive? Why don't you pause the video? Meanwhile, we can work through this. We know that the Coulomb attraction is equal to the constant K times Q1 Q2 over R squared in the R hat direction, which in this case is equal to -1 Coulomb times +2 coulombs divided by 3 meters squared times K. So we end up with -2 over 9K. We know that the units of force are newtons, which it's not perfectly clear by the units in the problem, but if you look this up you would find that the units of K and all these units here would cancel out and you'd wind up with newtons or something equivalent to newtons. We also know that this force is attractive because you have opposite charges. This negative sign indicates an attractive force. Now let's try a different problem with electric field and voltage. Let's say there's a positive charge, 3 coulombs, sitting 6 meters away from you. You're sitting at this point P here. Can you calculate the electric field and electric potential you would be experiencing? Make sure to specify the direction of the electric field. Why don't you pause the video and work on this for a few minutes? Alright, let's calculate the electric field. Electric field is equal to K Q1 over R squared in the R hat direction. So we know that the direction of this electric field is going to be this way because the electric field around a positive charge points outward because a positive test charge would move away from this central positive charge. So in this case, that's equal to K times 3 coulombs over 36, which is 6 squared. That's in the R hat direction. For the voltage, that is equal to K Q1 over R, which is a scalar, so we don't have to worry about the direction. And in this case, that's equal to K times 3 coulombs over 6 meters. So let's talk about units. Electric field strength is measured in newtons per coulomb. The electric potential or voltage is measured in volts. Let's try another problem. Let's say you have a charge of -2 coulombs, which is 2 meters away from a charge of -4 coulombs. Can you calculate the force between these two charges in its direction and the electric potential energy of this configuration? Let's give this a go. You know that force by Coulomb's law is equal to K Q1 Q2 over R squared in the R hat direction, which in this case is K times -2 coulombs times -4 coulombs divided by 2 meters squared, so we get +8K over 4. The positive here indicates that the force is repulsive, which makes sense because these are like charges. So let's calculate electric potential energy, which we know is equal to K Q1 Q2 over R. This is a scalar, so we don't have a direction. This is equal to K times -2 coulombs times -4 coulombs divided by R, which is 2. So we get 8K over 2. So let's look at units. Units of energy are always joules. So our electric potential energy is in joules, whereas the force, again, is in newtons. Now let's do some quick concept review. Let's say you have an insulating sphere with some kind of positive charge on it. How would this positive charge be distributed? Would the electric field be 0 within the insulating sphere? Well, we know that in an insulating sphere, the charges are fixed, so they can be distributed throughout the sphere, like this. May or may not be evenly distributed. And we know that the electric field since there are charges distributed throughout the sphere, does not have to be 0. How about a conducting sphere? Can you give a description of how a charge would be distributed in a conducting sphere and the electric field within the sphere? So if we have some kind of charge, positive or negative, on a conducting sphere, it will be driven to the surface of the sphere so it can get away from itself. This charge is able to do this because in a conductor it can move freely. This means that the electric field within the sphere will be 0. That's all for now.